Audio Jungle.
Now, let's begin with calculating for the speed at a particular point when you are given a problem like this. For instance, assuming this one is more like a mountain, let's consider this one to be a mountain. So the height of the bead at this point is represented as h1. How's the height of the bead? Now, for this particular question, they are asking you to calculate the speed of the bead at this point. And for sure, at this point, the B2 is also having a height. So let's consider this height to be height 2. Now, with this scenario, we will be able to calculate the speed at point B. Let's consider this point to be point A, point B, and point C. At point A, the bead is having a particular speed that enables the bead to actually roll down from this side all the way to point C. So if you are asked to find the speed at point C, let's try and look at the relation between it, because we know that energy can neither be created nor destroyed, but it can be converted from one state to another. So if you are having the bead at this point here, because the bead is also possessing a height, then it is having a potential energy, because potential energy is equal to our mgh, which is the height. So if the height is not 0, then it means that the object is having a potential energy. But at point B, the height is 0. So at point B, there is no potential energy. At point C, the height is also not 0. So at point C, the object is also having a potential energy. For that matter, we can look at the relation. When the ball starts rolling, the moment the ball gets to this part, this is the part where the ball will get its maximum speed. It will get its maximum speed because at that point, all the potential energy has been converted to kinetic energy. And if kinetic energy is very high, the speed is also high. Now I come to look at the relation and how to find the speed at point C. We are also going to know that the mass of the object will not also be important. For a particular question like this, we break it into two parts. We take point A and point B. Look at the relation between point A and point B. After that, we take point B and point C. Also look at the relation between it. So now let's delve into it. So at point A, we are having, let's say it is having a speed V1 is equal to 2 meters per second. So automatically it is having a kinetic energy as well. So between point A and point B, so mechanical energy at point A is equal to mechanical energy at point B. Remember that energy can neither be created nor destroyed, but it can be converted from one energy to the other. So here, the sum of energy, the potential energy plus the kinetic energy here, is the same thing as the amount of the mechanical energy comprising of the potential energy and also the kinetic energy at point B. So at point B, if the mechanical energy is only equal to kinetic energy, then this means that potential energy is 0. It is 0 because your height, there is no height here. So potential energy is 0. So at point A, we are having half mva. The va here represents the velocity of the object at point A plus our mj ha. The ha here is the same thing as h1. Now it's equal to, you remember that kinetic energy, this one plus this one, is the same thing as kinetic energy plus potential energy, which is the same thing as mechanical energy. It's equal to the mechanical energy at point B. So at point B, we are having half mv b square, remember this one is square, plus mj hb. Here, this one is what? Height at point B. Now height at point B is 0. If height at point B is 0, then everything here goes to 0. So now we are having our half mva square plus mjha is equal to half mvb square. Now this is what we are having between point A and point B. This is the relation that we are having. Now the reason why I'm trying to say that the mass is not important is that we are having mass here. We can factorize mass out. If you are factoring mass out, then we are having m, then half va square plus jha is equal to our m, then half v b square. So this is it. Then from there we can cancel our mass out. Yes, you can cancel mass out. So mass is not important. As you all can see, the mass will cancel out. So if they give you a question and they ask you to find the speed and they don't give you the mass, note that the mass is not important. You have to get the relation down. Now we can clear this fraction. If you are clearing this fraction, they are going to multiply each term by 2. We are having something like half 2 times half, then va square is equal to, no, plus our 2 times jha is equal to our half times 2vb square. So with this, we can cancel the 2 out and we are having only a simple relation. So these 2 will cancel out. Now we are having va square plus 2jh is equal to our vb square. Now this is the relation. So it means that if you want to find the speed at point B, then we just make vb the subject. So vb is equal to the square root of va square plus 2jha. So this is the relation between what? Point A and point B, and we can find the speed at point B. So if you can find the speed at point B using these two relations, then we can also take point B and point C and also find the relation, and with that we'll be able to find the speed at point C as well using the same relation. So with this, we are going to make it very simple. So let's write this relation down here. Let's write this relation VB. Now VB, let's write to VB is equal to VB square is equal to VA square. Remember this one is VA square, so VA square plus 2JHA. This is the speed at point B. Now let's try and find the speed at point C. At point C we can also do the same thing. Now let's clear it. So at point B and point C, the mechanical energy is still the same. Energy can neither be created nor destroyed. So we are still having point B and point C. Then at point B, we are not having any height. So at point B, our potential energy is 0. So our mechanical energy alone, which is mjhb plus half mvb square is equal to half mvc square, which is the velocity at point C or the speed at point C plus mjhc. So at point C we are having a height, so our potential energy is not equal to 0. But our point B, we are having our height here to be equal to 0. There is no height here. So point B, our potential energy here is 0. So now half mvb square is equal to half mvc square plus mjh at point C. Then our mass too is not important. We can cancel the mass out. So we are having our mass here, so all these masses will cancel out. And we can also multiply through by 2. Multiplying through by 2, then you are going to have half times 2 will give you 1. So VB square is equal to our half. No, this half to also cancel out. So now we are having our VC square plus our 2JH at point C. So if you want to find the velocity at point C, then the velocity at point C will be equal to the square root of VB square minus 2JH at point C. So this is the relation that will help you find the velocity at point C. Now, looking at the relation, we are having VB. This one is VB. So this one is VB, and we are also having VB here. Then why won't we make our calculation very simple by just substituting the formula for VB also here? We are having VB square here. So VB square is the same thing as this one. Then we can make the calculation simple because our VC is equal to VB square. Then wherever we see VB square, let's put VA. So now we are having our VA square plus 2JHA at minus 2JHC. This is the overall relation. But this relation, this means that we are having 2J here. We are having 2J. Let's factorize 2J out. So our VC, our velocity at point C, will be equal to the square root of VA square, which is the velocity at point A square, plus our 2J. Now the height is the only thing that is different, so our HA minus our HC. So this is the formula that will help you out. This is the shortcut that will help you out find the velocity at point C, or the speed of the object at point C, given the velocity at point A alone and the two heights. You'll be able to solve questions like this. So with a question like this, all you have to do is just use the shortcut that I taught you earlier. They said find the speed at point C. So at point C, if you want to find the speed, then you represent it by VC. So VC is equal to VA square plus your 2 times the gravity, then your height at point A. So height at point A minus your height at point C. Then you use this relation. If you are using this relation, you are having your VA. Your VA is actually 9. So 9 square plus 2 times 9.8. Then your height at point A, which is the 140 centimeters, you have to change it to meters. So it will be 1.4 meters minus the height at point C, which is 80, so 0.8. Then from there you do your normal calculation. So this is the perfect shortcut that will help you understand everything. All under the square root. With a normal calculation, you are going to get 9.6 meters per second. So this means that the velocity at point C is always what? 9.6. With this particular question, the velocity at point C is 9.6. And always note that the velocity at this point is greater than the velocity at point C, like I taught you earlier. So this is how to go by any question at all. No matter how they give you the question, automatically this side it will be having a value for the velocity. That will be velocity at point A. And if your height here is 0, this means that there is no potential energy. Potential energy at this point is 0. But here, your mechanical energy is what? Your potential energy plus your kinetic energy. And also the same thing at this side. Potential energy plus kinetic energy. At the end of the day, mechanical energy at point A is equal to mechanical energy at point B is equal to mechanical energy at point C, where your M is equal to your mechanical energy. That's all. That's how we solve questions like this. So no matter how the question has been given to you, or no matter how it has been framed, use this shortcut. If only your velocity at point B is 0, and always the velocity, if only the height at point B is 0, and always the velocity at point B, so VA or VB is greater than VC, because at this point, all what you are having here is your mechanical energy. So you are having your greatest speed at point B. The moment the ball starts climbing up, the speed starts reducing because it's now gaining a height. So now we are gaining potential energy at the same time kinetic energy, which sum up to give you the same mechanical energy that you were having at point B. The same thing applies to point C. Yeah, so now we are looking at the spring energy or the elastic potential energy. So this is the energy that is actually found in a spring or a string when you actually stretch it or compress it. For instance, if you are having a normal coiled string, This is the original length of the string when it has not been stretched or compressed. So original length. Now you know that you can stretch a spring, right? So if you stretch a spring, and this is the original length. Now if you stretch it now, you are going to have an extension. So this is the extension. Let's represent the extension as x. So our x here is extension. Then the moment you stretch the spring or you compress it, there is an energy that has been stored in this spring or string. Now we can find the energy, and you know that through the work and energy theory we can find the work done that is done by stretching or compressing the string. So if you are having an extension, force in a string is given as our spring constant times your extension. And you know that work done is equal to force times distance, right? Here we are not using distance, we are using extension. So our work done will then be equal to our half times our force, then our distance. And our force here is what we have as kx. So, and our distance too is what we have as our x. Then our work done is equal to our half kx times our x. So now our work done is equal to half kx squared. So if you want to find the work done that is being done by a string, then we can use the relation half kx squared. You can also use the triangular method. Using the triangular method, we know that the work done by a string, or using the graph method where we are having your force and also your distance. Then if you are having the force to be at this point and you are having your extension to be here, then you can trace a line. Now the shaded area is more like a triangle, right? So the area of the triangle is the same thing as the work done by compressing or stretching a spring. And you know that area is equal to our work done, and our work done is also equal to half times breadth times height, right? That is the formula for finding the area of a triangle. Then we know that our breadth is also the same thing as the extension, our height is the same thing as the force. Then our area will be equal to half times our force times our distance, which is the same thing as half kx then x. And in other words, it will still bring you back to work done is equal to half kx squared. So this is the relation. Use it to find the work done by compressing or stretching a spring in an elastic material. Elastic material can be anything at all that can be stretched or can be compressed. So now let's try and look at the relation between elastic and potential energy, or let's look at the relation between the spring energy and let's say kinetic energy. For instance, if you attach an object to a string and you release it, remember that all the spring energy is going to convert to kinetic energy. That will enable the object to move from one point to another. Now, looking at this scenario, we are having a spring that has been compressed by a block. So this is a block, and this block has compressed the string. Now, the moment you release the block, you are going to realize that the block is going to move in this direction. So before you release the block, all what you are having here is your spring energy or your elastic potential energy. That is the only thing that is being stored here. The moment you release it, then all the spring energy will be converted to kinetic energy. That will enable this block to move up to this point. So you know that mechanical energy or energy cannot be created or destroyed. So your energy at point A is the same thing as your energy at point B. At point B is when the spring has been released to allow the block to move, and at point A is the initial situation where we are having the spring being compressed. If you compress a string, then we know the work done, or we know the energy that is involved in it. So our energy here is what? Half kx squared. Do you get it? That is the initial point, or energy at point A. Energy at point A, we can even include the potential or the kinetic energy of the object, which is half mv squared. But you know that the energy at point A, the kinetic energy at point A is 0. Kinetic energy at point A is 0 because the object is still at rest. The object is not moving. But I'm writing it there so that later I cancel it out. Then you realize what I'm doing. Then it's equal to the energy, or the total energy at point B, or the total energy after the spring has been released. After the spring has been released, you are going to realize that all the energy has been converted. The string will go back to its original position. So you are going to have your half kx squared and also plus your half mv b squared. The mass of the block, the m represents the mass of the block, so there is no doubt. Then at point A, all what you are having is what? Only your spring or your elastic potential energy, because the object here is at rest. VA is equal to 0. If VA is equal to 0, then 0 times anything here will still give you 0. Now at point B, when this spring has returned back to its original length, if it returns back to its original length, then your extension, there is no extension. So extension at point B is also equal to 0. Then kx, 0 times any number here, will still give you 0. So now we are having our kx, our half kx, to be equal to our half mv squared. So with this relation, the mass of the object is actually important, because we have to be given the mass of the block in order to determine the velocity of the object. So the spring constant is actually a constant that they will give it to you in order to allow you do your calculation, and also as an extension as well. So if you are able to know the value for the k and also the value for your extension, the extension is actually given in centimeters, but make sure you convert it into meters. Very important, make sure you convert it into meters. So now if you want to find the velocity of the object after the spring has been released, then you know that this one and this one cancel, right? So now we're going to have our kx squared to be equal to our mv squared. Then we make v the subject. If we are making v the subject, then our v will be equal to the square root of kx squared divided by our mass. So if here you can even factorize the x out, but if you maintain it this way, this one is very important and this one is also nice. So I'll be posting some questions inside that will help you understand how to calculate for the velocity immediately after the spring has been released. So I'm come to summarize everything up. Here at point A, the spring has been compressed by the block. So before the spring returns back to its original position, it will actually push the block. So after pushing the block will also be having a velocity whilst there is no spring energy. Then from there, you use the normal relation that will help you also calculate the velocity. So this is the formula for finding the velocity of the object immediately after the spring returns back to its original position. You all know spring. Spring is something that you're meant to compress it and you release it. If there's something attached to it, it is going to push the object. So also we are going to find this one, there is only what? Kinetic energy and spring energy. Now we are going to find a relation where we are having kinetic energy, spring energy, and also potential energy as well. Now, for a question like this is a typical example of energy conservation, where they are asking you to calculate the speed at point B. So the scenario of this question is we are having a spring which has been compressed by a block here. So immediately, the moment the spring is being compressed, automatically it is having an extension represented by x. The moment the spring is being released, it's going to push this block all the way up. Remember that if it is pushing the block all the way up, it is having velocity. That is why it is moving. And also, it is moving at an inclined space, so it's also having a height. So at this point, the object is having a velocity. At the same time, it is also having a height, which is potential energy. So here it's having potential energy at the same time kinetic energy, but there is no spring energy because your extension here is 0. So at point A, energy at point A is the same thing as energy at point B. So total energy at point A is the same thing as total energy at point B. So at point A, you are having spring energy. So you are having your half kx square plus your mv square A divided by 2. I know it is 0, but I'm still writing it so that it will help you understand what I'm doing. Plus your mgh. You know that here your height 2 is also 0, but I'm still writing it. It's equal to, at this point, we are not having spring energy, but I'm still writing it. So half kx square plus our half mv square at B plus our mjh at point B. So this is it. Now, this is the total energies that are actually involved. So with this, you can cancel out your kinetic energy because there is no energy here. The same way you can also cancel your potential energy here because there is no height at point B. So the only thing that you're having here is your spring energy, which is, so your total mechanical energy is the same thing as, or your total energy at point A is the same thing as your spring energy. It's equal to, now at point B, you are having the object still moving, but you are asking you to calculate the velocity at point B or the speed at point B. But you don't have any spring here, so your spring at point B is 0. But because it is having a velocity, your kinetic energy will be there. So half mv square at point B plus, because you are having a height also, the object is having a height, then it possesses potential energy. So mg hb. So this is the energy relation here. So the more you practice it, you'll be able to just write the equation straightforward that, no, for this particular question, your spring energy is equal to your potential energy plus your kinetic energy. At this point, the mass of the block is important because the mass will not cancel out. We are not having mass in spring energy. So you have to be given the mass, and because we are having it, we can clear the fraction of by writing kx square is equal to mv square at point B plus 2mj hb. Here you can factorize the m out. Yes, you can factorize the m out, but if you factorize the m out, it doesn't actually change anything. You can factorize the m out to give you your m, then bracket open, vb square plus 2jh at point B. So this is the equation. If only you are finding for the mass, fine. But if you are not finding for the mass and you are finding for this, then you can. So the question is, find the speed at point B. So finding the speed at point B is this. So you just have to make VB the subject. So your VB will be equal to your kx square divided by your mass minus your 2jh. Your 2jhb. I don't know that the camera can capture that side. Yeah, so your 2jh at point B. Then because it is a square, you make everything the square root. So this is the formula that will help you find the velocity at point B. And it's very simple. You can find the energy relation at every point, whether it is a slope, whether it's actually an inclined plane or anything at all. You can find the energy relation here. Because at this point, even if you have been given the angle will not be needed here because as you are climbing up, your kinetic energy is reducing whilst your potential energy is also increasing.